Backward scheme, backward in time is implicit scheme. It's like backward Euler is L stable, unconditionally stable. Forward scheme is unstable. The time step, you cannot jump too quick in time. It's limited by CFL condition. Courant, Friedrich, Levy condition. Okay, CFL condition, basically, your time step must be small. Okay. If your space grid is big, your time can be a little big. But if your space grid is small, your time has to be even smaller. Look at this. Delta means like, here is not the Laplace, okay? Here is not Laplace, here is just like section or grid after you do discretization. The jump in time divided by the space grid square must be less than a certain constant. Most of the time that constant is 1, or sometimes 0.5, we use 0.5, or basically whatever it is that makes it stable. And you will know if it's not stable, your answer, you won't get the answer if it's not stable. So this means if your delta x is 0.1, 0.1 square is 0.01. So this means delta t has to be less than 0.01, right? Dimensionless time, dimensionless delta in time, and dimensionless x squared. Okay. That's a relationship. If you don't do this, the answer is not stable. Not stable means you get something like infinity or divided by 0 or something. And it is not your fault. It's not because you did something wrong in your code. It's because the algorithm itself is unstable. Not about the programming part. Alright. So do the substitution. T at n plus 1 minus t at n divided by delta. Everything defined at I current point in space. The right hand side is d squared by dx squared, right? Everything defined at n current time, but different I. I minus 1 and I plus 1. If you recall, we have this kind of formula. Minus 1/2, no. Second derivative, 1 minus 2 and 1. Right? 1 minus 2 and 1. That's for second derivative. 3 point. What do I have? I have 1 minus 2 and 1. And divided by delta x squared. Right? So that's, just use that table. Substitute value, we get this. So everything defined at n current time step. So this one, okay, is forward scheme, right? Forward scheme I have, from the table of forward scheme I have minus 1 and 1. So minus 1 is for the current point, so I have minus 1 over here and 1 over there. Good? Rearrange it, do some math, a little bit of math. So we say the dimensionless temperature at the next time at point I depend on the temperature at the previous time of point I minus 1, point I, and point I plus 1. So basically we have temperature. Okay. So this is capital T, and this scale is time. So if you want to know this point, green one, at the next step, you need to use these three. 1, 2, 3. It links like this. You get my point? To get 1 in the next time step, you need history of 3 points. Make sense? If you look at the formula, 1 in the future needs history of 3 locations. So delta t tilde by delta x square 1 minus 2 delta t tilde divided by delta x square. So that's just a coefficient. Okay, after we do some math. And of course you can do this, right? You will. Yeah, it's easy. Okay, what about this point? This point will link to that point and the boundary and that point. Do we know the temperature at the boundary? Yes, we do for initial condition. What about this point? How do we calculate the temperature at the next step at the boundary? George, help me please. How do you get that?
Discretizing it.
Oh, okay. You put some like technical word there, but doesn't help me much. Okay, that point. We discretize, yes, we discretize the boundary. Some boundary just say, hey, at x equal to 0, temperature equal to 1 all the time. Do we have that? At x tilde equal to 0, t equal to 1 all the time. So we don't need to do any calculation. So that point is just 1. Right? Just 1. But what about another boundary? This boundary. How do we find that point? We use the boundary condition, right? The boundary says partial derivative of t tilde with respect to x equal to 0. So that means, so when you do discretization, when you do like find a difference, you get some kind of this formula, right? Equal to 0, right? So this means t equal to t, but this is in time, that one will be in x. So if you do the formula for this formula, after the discretization, you get t b minus 1 equal to tb, like that. So this part actually it has to be delta x tilde, okay, not just x tilde, it has to be delta x tilde. You got it? So this is a backward scheme for the boundary condition. Make sense? Maybe too easy. So you say, hey, this point is the same as that point. So this is how you get the value at the boundary. And then you can do next time step. So if you want this point, you need the history. If you want to do this point, you need 3 history. If you want to do this point, you say it equal to 1. If you want to do this point, you say it's equal to that point. And you keep doing it, like marching operating. It's not stable. The jump has to be small. If delta x tilde equal to 0.1, this jump has to be less than 0.01. Probably maybe 0.002 or something. Put that in the code form, use that idea, solve it, and after you solve it, you get a bunch of number, which is not fun. We have to look at it. How do I plot this kind of plot? Did I teach you how to do this before? What is the name of the function to do it?
Name of function.
Yeah, it's from that matplotlib, right? What function from matplotlib?
You mean show the color?
To make this show up.
Counter.
Huh?
I don't know.
Something color?
Counter or something.
Counter, no, I think it is.
Surface.
What about p color? The function name is p color.
Yeah.
You remember?
Yeah.
So when you use p color, you can plot this. And how do I get the color bar? Color bar. Right? So as you notice, the grid on the dimensionless time is finer than the grid on the dimensionless X. That's why you see kind of strip of color like this. If you don't do this, it crashes. Because this is CFL condition. Okay? So when you look at this, ask yourself, is the answer correct? Probably not very much. Right? Because how come everywhere from point 2 to point 3 has the same temperature at the same time? Cannot be like that. But it is like that because the way we discretize. If we don't discretize like that, it's a violate CFL and it crashes. It's not good. But it's okay. If you want final solution on X, let's say you want 10 times finer in X, you must do 100 times finer in T. So if you want 10 times smaller grid to make your answer more accurate, you end up moving 100 times slower. You cannot cheat, right? If you want 1,000 times finer in this direction, you have million times slower. So in some application, like long duration of simulation, forward scheme is not the choice. You just cannot. Whether you like backward or not, probably you don't like backward scheme, but you cannot do this. If you keep doing this, it doesn't work. Okay, we get the solution, but the solution is in dimensionless form. Now we have to transform it back to the dimensional form. So I go back to my formula. I have alpha divided by b minus a squared multiplied by t. So I go back to the relationship between t tilde and t, x tilde and x, t tilde and regular capital T. So by using this formula, I can map this thing back to the dimensional solution, right? So I have time as a second. Do I need to invert any matrix? No, I just need to use for loop. Because the next point needs just that point, that point, that point. The next point needs just that point, that point, that point. And then I do the boundary at the last. Just that. I know you can do it. Can you? Conceptually, you get it, right? Okay. To not scare you, let's take a look at code a little bit. Okay. This one, you see, maybe you don't see. P color, that's how I got this. You see? That's P color. Okay, the code. Forward heat, not many lines, and I have just one for loop. The temperature in the battery and temperature at the left battery, right battery, I keep update layer by layer and go to the next layer. I mean next time slice. Keep moving in time. Done. That's a forward scheme. Okay. So with just this, what else can we do? You know, the solution of this kind of thing is already available in textbook. Right? You have the graph of the dimensionless temperature something for the constant temperature battery, which is they call direct link, and constant flux or Newman condition. This kind of thing already available. What is the benefit of redo this? Anything that we can tweak for the homework or for the project? What if this is constant property, right? K, thermal conductivity is the same everywhere. What if, okay, from the common equation you see alpha? Alpha is what? K over rho Cp, right? What if K changed from one location to location? Can you do it analytically? You cannot. Let's say your thermal conductivity go up linearly, and we want to calculate heat transfer, because thermal conductivity change with location. You cannot do it analytically if the function is crazy, but you can do it numerically. What do I change? Any clue? None? Huh?
No.
Has no answer. So when you have the equation, this means different location. You have different value for alpha, right? Okay. So this means you can discretize it in the dimensional form too. But if you discretize it in the dimensional form, what do I do for this? Alpha. So this alpha will be defined at point I. Right? See my point? So even though you can write every equation in this kind of form, this kind of final form, but every I will have its own thermal conductivity or its own alpha. So this means your governing equation, this equation change with location. Because the coefficient T tilde, what is T tilde by the way? T tilde is alpha divided by b minus a squared. So alpha is k over rho Cp. K change with location, this means alpha change with location, this means delta T tilde change with location. So delta T tilde at I minus 1 is not going to be the same as T tilde at I. T tilde at I equal to 1 is not the same as T tilde as I equal to 2. It's not the same as T tilde equal to I equal to 3. But you can still write it in this kind of form. You just have to tweak a little bit in the code, right? You have to do something in the code. Any idea how to do it in the code? You can still say delta T tilde at I minus 1, delta T tilde at I, delta T tilde at I plus 1. But you have your own definition of T tilde. Is it like that? Can I just do that? No. You have to start from the beginning. You get my point? Probably I'm right. I think probably I'm right. But what if I'm not right? There's no guarantee. You don't trust me. You redo it for your case. So this equation works for every grid point. Every 3 dots, this equation works, right? You have 3 dots. Another 3 dots, another 3 dots. Each 3 dot has its own delta T tilde. But hey, come on. Can we actually discretize it unevenly in time for every dot? Agreed. Do you mean if I have my space, do you mean, hey, this point move faster than this point, even though it is at n plus 1? No, I don't mean that. So this means you solve it from dimensional form. Got it? Sometimes, if you can solve it in dimensionless form, it's nice, but you can solve it in dimensional form. Make sense to you? Dimensional form means you do this kind of thing, but this time you have alpha over here, and that alpha will be defined at I and at n, to be easy. Okay. However, this kind of equation, you can take alpha out from d squared by dx squared only for the case of constant material property. Only for the case of constant alpha. If alpha is not constant, you actually get d by dx of alpha dt by dx. Okay? This is for the case of non-uniform material property. But it's okay. So in this case, if you want to do d by dx of this term, I call it big O. So you can do, hey, big O at I what? Minus 1 and what? You have minus plus big O at I. If you use forward scheme, or if you use central scheme, you have plus 1 over here. And big O, you have to redo this term again. Okay. It's like use central scheme of first order twice. You can do it, right? Can you? But what if you just do this? You don't do something like that. Does it mean your answer is wrong? Yeah, it's kind of wrong, but it's not that wrong. But it will be approximation, but not as good approximation as that. Especially for the case where your material property change with space. Okay? How do you do this twice? dt by dx twice. Any idea? So you can use central formula. You use that formula twice. At the end, you get something like that. Believe it or not, at the end you get something like that. Or instead of say, hey, d by dt, you put alpha in here. So we don't assume anything. We just put alpha in here. So when you describe t and alpha at the same time. And there's another alternative of doing this. Okay. So if you put t and alpha at the same time, you have 1 multiplied by t alpha at the point minus 1. Minus 2 multiplied by t alpha at the point of 0. 1 multiplied by t and alpha at the point 1. And you get second order derivative. Or if you do this thing twice, you actually get that. Okay? Anyway, you get approximation. Okay? Whatever you do, you get good approximation. So now maybe if you ask, hey, why don't we just use analytical solution if it is already available? Oh, yes, it is. But what if your material property is not constant? That's why we can do better approximation this way. Okay? If you want better approximation, we have to use finite volume. Finite difference give you okay approximation for the case of the material property change. But it's not won't be as good as finite volume. It's not be as rigorous as that. But by the way, do that. Okay. Okay, that's a forward scheme. What about backward scheme? Everything is the same. So I show you for the dimensionless form. You may have to do for a dimensional form by yourself. Except the right hand side defined at n plus 1. So everything on the right hand side is unknown. We don't know temperature at n plus 1. N plus 1 at I, we don't know the temperature at the next time step yet. We just know the current point. So this means you are doing something like this. 1, 2, 3. 3 points in the future linked to 1 point in the past. But we have 3 unknown. And one equation, how do we do that? You cannot. I cannot. Maybe you can, but I cannot. So we have to do this several times. So this system is one equation, right? Which is this part. One equation with 3 unknown. I can have second equation linked from this way, this point, middle, and that, and the bottom. So I use 3 points in the future and 1 point in the past. So that's the second equation. And I can have another equation over here. Third equation linked from that, and that. 3 in the future and 1 in the back. Oh, I have 1, 2, 3, 4, 5 unknown. So I need equation at the boundary. So at the boundary, I know that, hey, that point equal to that point. That's another equation, right?
Yeah.
Equation number 4. And at that edge, hey, that's equal to 1. So right now I have 5 equations, 5 unknown. I can solve it somehow. If it's linear, it is linear. I may just use, is it tridiagonal matrix? If it's tridiagonal matrix, I should use Thomas. If I want to do it slow, maybe I use LU decomposition. Okay. If I want to do it fast, maybe Thomas. So after we rearrange it, we get, minus R pop up. Minus R is just delta t divided by delta x squared. And Q pop up. Q is just 1 plus 2R. So what I'm saying is, after we do the math, from that, we rearrange it. Everything that is on n, I put it on the right hand side because it's known. Everything that is unknown, which is defined at n plus 1, I put it on the left hand side. So after you do the math, you get minus R, ti minus 1, plus q, ti minus r, ti plus 1. And they define at n plus 1. We have equation in general. The next step is, computer cannot work for something in general. You have to tell it step by step what exactly it is. We convert that into kind of matrix form. The boundary condition at x equal to 0, t tilde equal to 0. So I say, hey, t0, which is at point 0, equal to 1. I'm sorry, t tilde equal to 1. So t0 equal to 1. That's my first equation. Okay? So that is for the point on the boundary. So the next point I have minus r, ti minus 1. So next point means I equal to 1. I minus 1 is 1 minus 1 is 0. Right? So I have minus r multiplied by t0 plus q multiplied by t1 minus r multiplied by t2 equal to t1 at the current step. Everything on the left is at the next step. Where does this equation come from? I mean, previous slide, right? Yeah, this comes from previous slide. This is just, in general, here I just substituted. What if my I equal to 1? So if I equal to 1, I put 1 over here. 1 minus 1 is 0, 1 plus 1 is 2. You know, for master student, I don't imagine I have to teach 1 plus 1 equal to 2, but I said that, I'm sorry. Okay. So we have that. What if I equal to 2? So you have 2 plus 1 is 3, 2 minus 1 is 1, and you have this equation. And so on, until the end is different. The boundary at the end, you have t at the last point equal to t at the point before, right? So basically, minus tmx minus 1 plus tmx equal to 0. Or tmx equal to tmx minus 1. But I can put everything on, every unknown on the left hand side. And guess what? Everything here, they are defined at n plus 1, which is unknown. But we are okay, we have the same unknown, the number of unknown and number of equations are the same. The right hand side is, the top is BC, the bottom is BC, and the middle is known, the previous history of the temperature, except the boundary. Change it to matrix form. It looks like tridiagonal. Thomas algorithm. Okay? You know how to solve this already. That's why we have to know. Okay, this case you use Thomas algorithm is fastest way that you can do. How many times that you are going to use Thomas algorithm? 1 time, 2 times, 3 times? Who want? George? How many times? None?
This depends on the
1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
This depends on the grade.
It depends on how many times that we want to progress in the time, right? So if we want just one snapshot in time, we do 1 Thomas algorithm. If we want the next one, I do another Thomas. If I want the next one, I do another Thomas. That may be the fastest. I don't know. For the question about fastest or not, maybe it's fastest. If your matrix is not just this, but it's sparse, you cannot use Thomas, right? You may need to use LU decomposition sparse. The good thing with LU is you just change the right hand side. This thing, you just do forward and backward substitution and it's done. Okay, but okay, let's talk about finite difference to not confuse you with any sparse happen later for 2D problem. So for this case, for backward finite difference, you have your matrix. You solve it, Thomas algorithm, kind of inverse it. Then you get the solution of the next step. You move that solution of the next step to the right hand side and you keep doing it. Keep inverse the matrix. Keep doing it. You get the solution. Look at backward finite difference. Okay. This is a dimensional form already after we substitute the value back. Look at it. The top one is not zoom in. The bottom one is kind of zoom in from 0 to 4 seconds. Which one is a backward scheme? The left. That one. How do you know that?
Written there.
I've written there. If it's not written there, you have any guess?
It looks fine.
Because you can do fine interval on both. Even though you discretize x very fine, you don't need to move slow. So for the case of forward scheme, you cannot discretize x very fine and you still have to move very slow. If you want it to be this fine, it will be too slow. Okay. But for forward scheme, it doesn't need for like matrix inversion or substitute of the equation. Okay. So backward scheme, typically backward scheme and forward scheme, they are at the same accuracy. But for finite difference problem that has CFL condition, backward scheme can be more accurate because you don't need to have the jump in x like that. So you have more freedom on discretization. It's easier. You can move faster even though you discretize the same finite grid. So I can see this side, I can see it curved, right? The right hand side I see as a step. Crank-Nicholson. Oh, we have 5 minutes left. Let's do Crank-Nicholson. Crank-Nicholson means you have forward Euler or forward scheme. You did it already, right? Forward scheme. Everything defined at n, and the right hand side look like this. Backward scheme, everything on the right defined at n plus 1. That's backward Euler. Backward Euler is this. So Crank-Nicholson, you have backward scheme. This one is backward scheme plus forward scheme divided by 2. That's Crank-Nicholson. Average between the past 2 methods, basically. Okay? And it becomes second order in time. It's more accurate. Is it unconditional stable? Yes. But the solution can have oscillation. So it's not really stable. It's stable, but has something strange happen. Okay. So you use 3 points in the future linked with 3 points in the past, right? And it's unconditionally stable, but can contain some oscillation if you don't satisfy CFL condition. Okay. So Crank-Nicholson, just the same math. You put it twice, rearrange it. You get this. This is just to make it easy, okay? Believe it or not, it's make it easy. So this side multiplied by that is kind of from forward scheme. This side is from backward scheme. So this kind of matrix come from after you do all the math. Okay? Because Crank-Nicholson is the average between forward and backward, right? When you do all the math, you get this. Okay? And Look at this one. Why is not minus 1 and 1? What do I do over there? Why do I have to do this? One thing to mention is, it doesn't, you won't want to do it like mix the different accuracy degree together. Or at least I don't want to do it. I know for sure that the accuracy of the total scheme is depend on the smallest accuracy. Let's say in space you have central scheme, right? That is second order accuracy. In time you do Cram-Nicholson, you have second order accuracy. But at the boundary, if you ever use first order accuracy at the boundary, your answer is first order accuracy. You see my point? So all the degree of accuracy has to be the same. Otherwise, your answer will be the lowest accuracy. If you ever contaminate your second order scheme with first order, everything is first order. Okay? So this part is 0.5 minus 2, 1.5, which is 0.5, always 0.5 minus 2, 1.5, did I do it wrong? 1.5 minus, oh, okay. I use something strange. Is that because of this? So I try to use I think I use backward scheme. 0.5 minus 2, 1.5 at the end. 0.5 minus 2, 1.5. 0.5 minus 2, 1.5. 0.5 minus 2, 1.5. Oh, I did it right. So I minus 2, I use 0.5. I minus 1, I use minus 2. I use 1.5. So I use second order accuracy backward scheme for the boundary condition on the right. That's why I have this. Right? And we just have one ODE. So this part we don't have anything. Due to kind of discretization, certified CFL condition, I get the step. Not certified CFL condition, I get the oscillation. Sometimes the answer go more than 50, which is the limit. It's bad, but it's stable. If you do this, just forward scheme, it just crash. You don't get anything. So Cram-Nicholson without certifying CFL, it's okay. With certified CFL, it doesn't have any oscillation. Okay. And later on, we will do 2D. For 2D, your equation is not tridiagonal anymore. It's got tridiagonal block matrix. You inverse it or something, and then you get this kind of thing. But we do that next time. And next time, if possible, we want to do Phoenix project, finding element, a little bit of math. And next Wednesday, we explain more about the code. And then we are done for this course. You do the project. Thank you for coming. 12:20, so I'm kind of 35 seconds later. Okay, bye-bye.
Thank you.